Okay, the last lesson was about the second derivative. So let's do a little recap of that, and we're going to talk about local maximum and local minimum today. Okay, so the notation for the second derivative is y double prime, or this, d2y over dx squared, or that's what it looks like anyway. So as opposed to the first derivative being dy dx. Just there's a it's just weird that the 2 is between d and y. Um, and if you think about like d dx of f of x is a notation, so d dx is the operation and y is the function, so you wouldn't square the function, right? Hope that makes sense. So it's these are the two most commonly used notations for the second derivative. All right, here's an example from your textbook, the Harder book, and it says, okay, here's a curve from it looks like x to the fourth graph of some sort. All right, let's identify when the graph is increasing, decreasing, or concave up or concave down. So I made these number lines down here so I can write down the signs of f prime or f double prime. And I can do that by looking at the graph, right? So if I look at from A to B, the graph is going down. So I know f prime is negative. And then from B to D, the graph is going up. So f prime is positive. And then from D to F and F to G. All right. So easily, I can find the sign of f prime from looking at the graph. And not as easy, but close enough. I can find the sign of f double prime as well. Well, I say that it's a little more challenging because you're not going to be able to find exactly when they change, right? So like C here, I'm giving you where the concavity changes, and E here, but normally you wouldn't know exactly where that happens. All right, so from A to C, you can clearly see that it's got this shape, so I know f double prime is positive there. And from C to E, f double prime is negative, it's concave down. And from E to G, concave up again, so f double prime is positive. So once I have those things, you should be able to identify them as well when you have the graph. You can find the local max and local min using those things. So here you can clearly see from the graph that the B is a local minimum, D is a local maximum, and F is a local minimum. And we say local because the opposite of that is global, right? Global minimum, global maximum. So if you have a quadratic here, and that goes on forever like this is both the local minimum and a global minimum because there's no other point on this graph that's going to be lower than this. So that's also a global minimum and a local minimum. And then for other graphs, like if you look at here, right, the highest point ever is A. So this is a global maximum, right? D is higher than the neighboring points, but it's not higher than everything on this graph. So that's just a local maximum. All right. So how do we do that? There are two different ways. One is using the first derivative. So if I look at B here, point B, I know f of B, so f of, or f prime of point B is 0. All right. Um, then f prime leading up to it is negative, which means the graph is going down. F prime after that is positive, which means the graph is going up. So I know that there is a local minimum at x equals B. At x equals D, f prime is 0 right there, right? So f prime of D is 0. So that's a stationary point. And to the left of it, f prime was positive, so the graph is going up. A stationary point at D, and then it goes down after. So I know there's a local maximum there. and then f will be the same thing because there's a minus and a plus sign there on the number line, so it was going down and up, so there's a local minimum there. Okay, that probably you already knew that. And now last time we talked about the second derivative. How do we use the second derivative to identify local max or local min? Right. So you still have to find the stationary points. So where f prime is equal to 0. So I found those, let's say, b, d, and f. And then you're looking at the sign of f prime at that point. Not before or after, at b, at d, and at f. Here, here, and here, right? So if you think about at x equals b, this f prime of b is 0, but the f double prime is positive, right? So at b, that would be right here, right? F double prime is positive. So you have a stationary point, and around it you have this concave up shape. So that makes this a local minimum. Similarly, at x equals d, the first derivative is 0. So that means there's a stationary point, and at that point, the concavity is concave down, or f double prime is negative. So that means you will have a local max, right? So you can use the sign of f prime or f double prime to identify the local max and local min, which is what today's lesson is about. All right, so I found this summary of what I just talked about. It does say it's a sign diagram test, but it's the first derivative test. That's what the IB will call it, right? Not the sign diagram test. It'll say draw a sign diagram, but the name of this test is the first derivative test. What do you do? Find out when you have a stationary point, draw a number line, sign of f prime before and after, and then you can see if it's a local max or min. The second derivative test is you still need this. You still need when the derivative is equal to 0. So those are stationary points. And then at those points, or at that point in this case, just one, if f double prime is less than 0, that means that you have concave down, and therefore you will have a local max. And at that point, if f double prime is positive, then your overall shape is concave up, and therefore you will have a local minimum. All right, so that's kind of what we're going to use today to find local max and min of different functions. All right, so this example is not from your textbook. It's from a different one, but it's good to kind of go through because these are polynomials and easy to deal with, and it's still like you can get the concepts from this. All right, so you have the function, and I want to find out all the points where f prime is equal to 0. So I'm going to do that. So part A, I need to first find f prime. What is that? 1848 plus 48x. Okay, and then I can factorize this. They all have x's and they all have factors of 12. Okay, and then I can factor out the quadratic inside as well. There. Okay, so when is this going to be 0? F prime of x is 0 at x equals 0 and 2. Cool. Those are the places where f prime is 0. And then B, I'll just change colors. When is it increasing or decreasing? So in this case, I'll just make a number line. And I'm going to use the sign of f prime. at these intervals. So I'm going to find intervals here, 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 and you can easily substitute a number in that interval and find the sign for it. So if I wanted to know if f prime is positive or negative here, I just need to choose a number that is less than 0. So let me think about like -1 or something, right? Um, Here, x minus 2 is going to be squared. So that's always positive, right? Always positive. So I don't need to think about the sign of this part of it. I just need to think about 12x. So if x is -1, it'll be negative. If x is between 0 and 2, that's definitely positive, right? Think about x equals 1, so it'll be positive. And then x greater than 2, again, will be positive. You can definitely do that, and then you'll be able to answer f is increasing when x is greater than equals 0. F is decreasing when x is less than or equal to 0. Okay, so that is how you answer that. Like, so you can figure out, from the number line, you can just kind of see. There is a little odd thing that I'm doing here where I'm including 0, so it's less than or equal to, greater than or equal to 0. That is correct, but at this point, I'm not going to explain like why that is. It's just and the IB will accept if you said f is increasing when x is greater than 0 and f is decreasing when x is less than 0. They'll accept this as a correct answer. So I'm not going to go into like too much detail about this, but this is a correct way to answer it. So in college or something, if you're taking, if you have to take college calculus, you will have to answer it this way. All right, part C. Find intervals where the function is concave up or down. So that'll require the second derivative, right? So f double prime of x is equal to, and I'm going to look at this, and then that's 36x squared minus 96x plus 48. And I think I can factor out 12. That's 3x squared minus 8x plus 4. And I should be able to factor that out as well. Let's see. Minus 2, minus 2. That works out. Okay, cool. So that means f double prime is 0. I'm going to draw this number line at x equals 2/3 and at 2. So I can figure out if f prime is positive or negative in these intervals, and I can answer that question. Now here's a little shortcut. I know a lot about quadratics. I know a lot about parabolas, and actually all, polynomials really. But this is a parabola that opens up, and these are the zeros. So that's the x-intercepts. So your parabola, if you were to graph it, will look like something like this. So I know, without substituting numbers in there, f double prime, the sign of f double prime is positive in this interval, negative between, and then positive after. So f is concave up for x less than or equal to 2/3 or x greater than or equal to 2, and f is concave down for x between 2/3 and 2. Okay, and the last question is find all points of inflection. Points of inflection, or a point of inflection, is when the concavity changes, right? So let me make these things a little bit smaller here. here. All right, D. So I've already done the work in part C because I drew this number line. So when x is 2 over 3, before that, or to the left of it, it's concave up, and then after that, it's concave down, right? So that's a point of inflection when x equals 2/3. And then again, at x equals 2, it was concave down before and then concave up. This f double prime changes signs. So that's also a point of inflection. And so it happens again at x equals 2. All right. If the question says find the coordinates, then you have to find the y values as well. And then you have to put, coordinates like 2/3, comma, whatever the y value is, and 2, comma, whatever. And when you do that, you would have to use the original function because that's the y value of the graph, not f prime or f double prime, right? So that's it. And from looking at this, you could even graph the function, right? So there is a minimum, right, at x equals 0. And you could tell by the sign of f prime because the f prime was negative before 0 and then positive after. Or you could look at this and say, oh, that's a stationary point, and when x is 0, f double prime is positive, which means it was concave up, and therefore you have a local minimum there. So you have a local minimum at 0, so it goes down at 0, and then it goes up, and there is a stationary point at x equals 2, but it's not a max or a min because the graph goes increasing again, right? So the function will kind of look like this, where these are the two stationary points, but you only have one local minimum. All right, well, graph it on Desmos or in your calculator and then see what that looks like. Okay, now that is a very typical max and min question or curve sketching question. I have a ton of those, and then you will have more work to do on that one. But the idea is the same. So like whatever the function, I can change the function, but what you have to do is the same. Okay, so optimization is the word problem for finding maxes and mins, right? So you apply the same techniques and same concepts into a real life problem, then that is called optimization. So you're looking for max and min. So this is a question that, or this is what your textbook gave as an example. So it says a business product produces X thousand units for a particular product each month where X is greater than 0, right? The profit P in thousands of dollars is given by this function. So find the number of units the business should produce each month to maximize its profit, showing that it is indeed a maximum, and then find the maximum profit. So what do you have to do? Find the derivative, right? So you find the derivative and then set it equal to 0. So you have this equation, and then you solve for x, and then you get x equals 4. Now here, at this point, you could draw a number line and say, okay, x is 4, and then try to find the sign of f prime, right? The sign of f prime, like just plug in numbers here. So I could do that, right? So I could put x equals 1 here, and I know that's going to be positive. And then when x is, I'm going to have to do something that I can, square the square root easily. So maybe like 25 or something. Then that's going to be 24 times 5 minus 3 times, 25 squared. That's definitely going to be negative. So at 4, it's going to go up and down like this. So I know that's the maximum. What your book decided to do is do a second derivative test. So the second derivative is here, and then when x is 4, you substitute x equals 4 and find that it is negative, and therefore there's a maximum when x is 4. So the business should produce 4,000 items per month to maximize their profit. And what is that profit? You substitute the value x equals 4 into the original profit function, and you get 39, and the unit was thousands of dollars, so $39,000 per month is the maximum profit. Cool. So that was nice. What was different about this question than what you will see in the IB exam questions for optimization is that the function was just given to you. So that's really typical for AI SL, but for AA, they're gonna make you come up with a function to differentiate and then ask you those questions. So what that might look like is not this one, but it is such a like such a like if I think about like optimization question, this is like the one of the first ones that I can think of. So I just decided to uh, share this one with you. Um, but the actual IB questions will be something like this one, where it'll say, hey, here's a scenario. I want you to show that area can be expressed this way. And then it'll say, find the dimension that maximize the area. So it'll be a show question most of the time, because if you can't get started without the equation, but they want you to figure that out. So I'll do this one first. Um, so there's a rectangular, like a piece of paper or like a metal sheet, and you are going to cut out squares from all four corners, and then you're gonna fold these here, 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 and make it into an open face box. So there's no like top here. It's just, I don't know, like a baking tray kind of stuff. What is the dimension of the square that you're cutting out that will maximize the volume of this? So that's the question. So it says show that this is the volume of this box, where x is the dimension of the square. Okay, so I'm going to show that. That's what I'm gonna, so here, I'll draw the same picture, and that's 40, and this is 25. And I'm cutting out squares of the same size, right? If you're gonna fold them up and they're gonna match up, they better be the same size squares. And I'm gonna call this this much x. So it's x by x, right? If that's the case, this much here would be 25 minus 2x, and this much here is 40 minus 2x. So when you make this into a box, right, this dimension is 40 minus 2x. This is 25 minus 2x. There. And then the height is x. So the volume is 40 minus 2x times 25 minus 2x times x. But I need to show that it's equal to 1000x, blah, blah, blah. So I'll just multiply the x first, and then I'll just say I get this. Cube. Okay. Now, that's part A, and then part B, it says find x that will maximize the volume. So I'm going to do that. I need to find dv dx. That would be 1000 minus 260x plus 12x squared. Okay. I think I can factor out 4. And now I'm just going to change the order. So that's 3x squared minus 65x plus 250 minus plus 250. Yeah. And then I should be able to factor out the quadratic as well. All right. That. Yep. Okay. So there's that. But I forgot to I forgot to do something right between part A and part B, which is talking about the domain of x. So x, because x is the size of the square, right? So it's got to be bigger than 0. But the biggest it can be is half of the shortest side, right? So it can't be more than the half of the shorter side. So the maximum that x can be is 12.5. And coming back to part B, when is dv dx equal to 0? When x is 50 over 3 or 5. But 50 over 3, that's more than 20, right? So that can't be it. Since x is 5. Okay. There, I would need to confirm that it is in fact a maximum, because having a stationary point doesn't guarantee that I have a maximum. It could be a minimum or it could be neither, so I should check. You can check however you like. I'm going to find the second derivative, so d2v dx squared is minus 260 plus 24x. And if I substitute x equals 5 in there, so when, okay, well, double prime of 5 is negative 260 plus 24 times 5, which is 120. So negative 260 plus 120, for sure that's negative, right? So it's negative. So the first derivative is 0. The second derivative is negative. So you have, it's concave down. So you have a local max. There. Okay, so this was a little different than the textbook question in the Hotter textbook, because you weren't given the function that you were supposed to differentiate and maximize, right? So you have to figure that out somehow. Started with a box, cutting out x's, and then always drawing a diagram helps, for, at least for me. And then you find an expression for the volume. Here, having some kind of a domain for x helps, because you saw that down here. You got two answers, and so you have to know which one is going to be. Sometimes it could be both, but this one couldn't be a possible answer. And then you confirm that it is in fact a maximum by doing either the first derivative test or the second derivative test. No question will be asked where you have to do one or the other. You just choose which one is easier for you, right? Okay. And the last question here, a very typical optimization question. I think this will be an easy question. Not this class, but next class on Tuesday, I'll be there in person and I'll give you some more challenging optimization questions. So here you have an existing fence. Sometimes it's a river, sometimes it's a barn, whatever, but it's a straight line. And you have some fencing materials that put up, to put up fences, and you're gonna make a rectangle like here, right? Using this existing wall or fence or a river. All right, and you have 60 meters of fencing material, and you're gonna build a rectangular fence or a rectangular area. All right, so part A, it says show that the area A here of the enclosed area can be expressed by this. Okay, so because it's a show question, you have to do more than just kind of rewrite the question, right? So that's going to be x, and this is x. Let's call this y. So the perimeter of the three sides is going to be 2x plus y, and we know that can only be maximum of 60 because that's all the material you have. So y can be expressed as 60 minus 2x. Okay, and the area of that rectangle is x times y, but y I can replace with 60 minus 2x. and that I have shown that the area is that. Okay, in part B, find the dimensions which maximize the area of the enclosure. So I need to find dy dx or dA dx. Okay, well, it will help actually if I just wrote this that way. dA dx is going to be 60 minus 4x. Okay, and when is it equal to 0? Is when x is 15. All right, so I found x equals 15 is when the derivative is equal to 0. So I still need to confirm that actually gives you the maximum. And I'm going to do this by doing this, looking at the second derivative. Right? It's always negative. It's always concave down. Therefore, maximum area is maximized when x is 15. But I'm not done because what the question asked, find the dimensions, right? So if x is 15, you got to figure out what y is, and you can quickly just do it. Here, y should be 30. So the dimension is 15 by 30. Is it meters? Yeah. 15 meters by 30 meters. Cool. And that's it. Yeah, so that's what today's lesson is. And the rest of this class and for homework, you can do exercise 20E, number 1 through 19, and number 21. It looks like this. So there's quite a bit. And then when you come down here, those are all the green and blue questions as well. And then number 21. The derivative is going to be a quadratic involving e to the x. So that's my hint. Okay, good luck.